the coalition formation mechanism that comes not only from Myrna, but by a large coalition of co-authors in this case. So Myrna, you have the stage.
Okay, thank you very much. Thanks to the organizers for organizing all this. I think it must have been as much work as organizing the conference in Stony Brook, even if you don't have to provide dinners. Let me introduce my co-authors a bit. Eugene is well, he was a professor in the computing science department here, but he's moved on to WashU. Greg Liu, you know, he's a faculty member in the economics department at Vanderbilt. And these are the students who participated in various parts of the paper at various times. Now, okay. So what do? We model, sorry. I have to look at my notes a little bit because I have my screen sharing slide shows up on my top line. Okay, so we model decentralized coalition formation as a sequential bargaining game with preferences over outcomes. And the main surprising actually result is if each proposer can make enough, but a finite number of proposals, then the SPNE, the subgame perfect Nash equilibrium, is individually rational and Pareto optimal. Why is this result surprising? Well, as far as we know, the main cited paper on sequential formation of coalitions of this sort is serial dictatorship. And in serial dictatorship, first person makes a proposal, okay, and then the other person, then the second person accepts the proposal. You have to accept the proposals made to you with serial dictatorship. And here you can we allow rejection of the proposal. So this work, as far as we know, is really path-breaking in that we have both individual rationality, which serial dictatorship doesn't have, and it's an SPNE and individually rational, right? Okay, so okay, the game. The game, we introduced what's called an accept-reject game. Yes, okay. This is good because I'm going to teach online in the fall and I'll probably learn more about Zoom from this. Okay, most or many of the papers, I say many instead of most because I probably haven't read most of them, make a consequential assumption about the order of proposers. The first proposer to reject a proposal becomes the next proposer. That's usually an assumption, as I say, usually made. Many start with the TU game. They start with the TU game and develop a bargaining procedure to obtain outcomes in the core. We start with an extensive form game. And I mention here a few papers in this line that start with a TU game and then try to support the core. Just a few of them there. So the game, as I said, is called an accept-reject game. And here are the components of the game, a bit of notation, a set of players, a set of admissible coalitions. An admissible coalition for player I must contain player I. You only can propose coalitions of which you're a member. Pi denotes partition of the total players set into coalitions. pi I is a coalition containing player I. We have preferences of I over admissible sets of coalitions to which they can belong, and then a preference profile. Okay, I'll remind you of various points of the various notation as we go along. So an accept-reject game is a game of perfect information in extensive form with the above components and an ordering over the players, including each player at least once. So the ordering determines the order in which players can make proposals to other players to form a coalition.
So, Myrna,
Okay.
there is no characteristic function here. It's just the primitive is an ordering on the coalitions to which you can belong.
Right. The primitives are the extensive form game of perfect information and the ordering over which players can make proposals. Okay. So this makes a game different from extensive forms, and it's not a TU game. It's an ordering where players just have preferences without a utility function. Okay. So here is a general idea. The first proposer makes a proposal to other members of some subset of players, say S. The members of S sequentially accept the proposal or reject the proposal. If accepted by all members of S, then S is formed and its members have no further actions. If one member of S rejects the proposal, then the next player in the ordering, who may be the same player, they can propose more than once, right? Can make a proposal. Okay, so let me give you a picture of this. Here's the picture. This is a simple two-player game where three-player game where only two players, or all coalitions have only two players. So, for example, we start with player one, who can make a proposal to two or three, or one can just propose to herself, but we haven't shown that. Right? We always allow a player to propose to themselves and then form a singleton coalition. So here, one can propose to two or three, and then two or three can accept or reject. If one proposes to two and two accepts, then the coalition 1-2 forms, and formally we should have now three allowed to make a proposal. But three can now only propose to himself because 1 and 2 are really finished in the game. 1 and 2 have no further actions. So three can only propose to yes. Three can only propose to herself if this happens. Now 2 could reject, and then 2 could propose to 1 or 2, or 1 or 3. And if 1 accepts, this coalition is formed, 1, 2, and 3 again has to form a coalition with herself. I don't know why this screen keeps doing that. My hands are here, I'm not touching anything. Okay, right, and it continues. If 2 rejects, then it's 3's turn. 3 is next in the ordering. 3 can accept the proposal from 2 or reject. If they accept, of course, then we get to the coalition 2-3 being formed and 1 by herself. And then 3 can reject because 3 now is three is the only player now who can propose because we're only allowing 1 proposal per player in this diagram. 3 can propose to 1 or 3 can propose to 2. Clear? Okay, now we want to look at the subgame perfect equilibrium for this. I should tell you, the little clouds, what's in the little clouds? The continuation of the game, which hopefully at this point, if you wanted to fill that in, you could do that, okay? But the page here is kind of small, and when you start to draw these extensive form games, they get very large, even for this simple example. But let's look at the subgame perfect equilibrium. Well, 1 proposes to 2 and 2 accepts. If 2 were to reject, 2 would propose to 1 and 1 would accept. Or 2, yes, and if we get to this node, 3 could propose to 3, or 3 could propose to 1 or 2, and we would get these outcomes here. So it's just really standard calculation of a subgame perfect equilibrium. Okay, questions?
Yeah, well, so just to double check, you a priori bound for each person the number of proposals he can make. So it's a finite tree.
That's right. It's a finite tree. Okay. So if it's a large enough piece of paper, we could draw the whole game tree. Right. Yes. For the special place, I'm not going to go through this slide actually, because if nobody has any questions, it just does or says in words what I said about the diagram. Okay, so it's easy to see that individual rationality is satisfied by the equilibrium of an arg, an accept reject game. And
I'm
we're
sorry,
going
Myrna.
to,
Myrna, I'm sorry, but I don't see any utilities, any preferences here. Where are the preferences?
You missed the first page.
right,
I
the
did?
first page
Yes.
had preference profiles, right.
The preferences are on the coalitions that you belong to. You have a strict ranking of them.
Okay, thank you. Thank you.
Right. So we make this assumption that players prefer to form a coalition earlier in the game rather than later. We can think of this as lexicographic preferences of a sense, or we could think of this as there being some discount factor, so they have an incentive to form the coalition earlier. In the picture, you saw that 2 could reject to the proposal of 1, and but then 2 could propose to 1. So we rule that out. It really simplifies matters.
Now I'm confused because there are no utiles here. There is just there are ordering. So
Yes.
how does discount factor work?
How does this affect the ordering?
Yeah.
Okay.
If
So
you had utiles, then you could take discounted sums. But you don't have utiles. You just have an ordinal ranking.
we have an ordinary ranking, right?
Ordinal, yeah.
We can make the assumption that for any preference profile, right, the player prefers the coalition and prefers to form a coalition earlier.
Rather, okay. But
We could easily put the details of that in, right? But
okay.
we didn't.
By putting pair.
So, and then you see that means the subgame perfect Nash equilibrium outcome is unique. And in a subgame perfect Nash equilibrium strategy profile, all proposals are accepted. Okay. Yes, all proposals are accepted in a subgame perfect equilibrium in every subgame. Okay. But a Pareto optimality is not necessarily satisfied. And I mentioned before serial dictatorship. Serial dictatorship is Pareto optimal, but it's not individually rational. Okay, so now we have an example, which is important in the motivation of the paper. And here are the preferences for a roommate problem with a set of 6 players. Okay. We needed 6 players to develop this counterexample, or this example, I should say. And we can see, in fact, I'll tell you that the non-Pareto optimal outcome is 1, 5, 2, 4, and 3, 6. Okay. Figuring that out is sort of standard but complicated, so I'm not putting it in here, and you all know how to do subgame perfect equilibrium. This one is not Pareto optimal. This one is a Pareto improvement. Why? Because 3 is still with 6. That's not changed, but 1 and 5 and 2 and 4 have switched partners, in fact, from this outcome. 2 is with 5, which they prefer to, yes, they prefer 5 to 4. Here they got 4, here they got 5. And 1 and 4 are both better off according to this preference table. Okay, 1 and 4. Now the outcome 1, 3, 2, 5, and 4, 6 is Pareto optimal. Okay. Now how do we get to that, right? Or how do, yes. So now let one make 2 proposals. Okay. So suppose 1 then proposes to 3. Okay. 1 can make 2 proposals. Suppose in their first proposal, 1 proposes to 3. And I claim that 3 will accept because 3 is better off with 1 than he is with 6, right? 6 is everybody's least preferred partner, okay? So 3 is better off in this outcome. 2 and 5 are better off because, as I've showed you before, 2 and 5 is a Pareto improvement. And 4 and 6 are together. Unfortunately for 4, but that's what it is Pareto optimal. No one can do any better. Okay. Now I want to talk about talking about why the 2 proposals matter. Why does 3 accept? Well, 3 accepts because if 3 rejects, the game now is the same as the original game with only 1 proposal. Okay, they can make 2 proposals. 1 proposes this. If 3 rejects, you get back to the original game, which is now a subgame when 1 can propose twice. And 3 then, or this the subgame perfect equilibrium of the 1 proposal game is a threat, or a credible threat to player 3. If player 3 rejects the first proposal, 3 will end up with 6. So 3 doesn't want that. So 3 accepts the first proposal when 1 can propose twice. 3 is the second proposal, the original equilibrium, okay, or the equilibrium of the original game is the threat. Okay? Questions? No. And this is one of the main ideas of the paper. The actual subgame perfect equilibrium of the original game becomes the threat. Okay. Of course, it may not be a threat if the original is Pareto optimal, but in this case it is. So the ordering of players and how many proposals players can make makes a big difference to the game. Amazingly. Right, so this is just going through what I told you before. Okay. So I won't go through it. Now getting to the core and getting to the core of the derived cooperative game. From any extensive form game, you can derive a cooperative game really by just looking at the endpoints as the coalition, or the payoffs to coalitions, or the coalitions that would be formed. And the coalition structures in the core if there does not exist a coalition of players such that all players in that coalition can do better. The core may be empty, of course. So in another paper, okay, we introduced the idea of an iterated matching of soulmates. And that's the idea that a set of players who, among the players not already in coalitions, all prefer to be with other are naturally matched. So compare this like to the top coalition property. Okay, this, which is much more restrictive, right? The iterated matching of soulmates allows some of the players to be matched as soulmates, right? While leaving the other players to form then their own, to proceed, right? So let me explain this a bit more. So imagine a situation where you have all the players in a room and you ask everybody to point to the members of their preferred coalition. If one of those coalitions is accepted, then those players who all want to be with each other are finished. They have no more actions in the game. They form the coalition. Two-person case, one player points to another, the other player points back to her, and that's the coalition, and they're done. They agree. Now there's a remaining set of players, okay? Given that some players' first choice may have left the game effectively, the remaining players can form a coalition of soulmates if there is such a coalition. Okay, any questions with that? Okay, good. I love it when people nod or go like this. Thank you, George. Okay. So iterated matching of soulmates matches all soulmates. So if iterated matching of soulmates matches all players, the resulting outcome is in the unique core structure. So if any players, if all the players are matched by this, then you have a core coalition structure. This is related to, again, the top coalition property of Banerjee, Kanishi, and Somnaz, which ensures, they impose a condition that ensures that all players are soulmates. The condition is much stronger than ours, but on the other hand, ours is closely related if you can match all soulmates. So suppose that all players are matched as soulmates, then every SPNE of an arbitrary accept-reject game yields a unique core coalition structure. Okay, and that's not hard to intuit in some sense, because it's a game of complete information, perfect information. So if we have soulmates, for example, people whose first choice are all choose each other as their first choice, then they will wait for a person in that coalition to make a proposal, right? I know that Pradeep would really like to work with me, right? But, you know, he hasn't proposed yet, but, you know, or given that John Giannakopoulos may be on vacation or something, then so Pradeep can't match with John, then I may be his next choice, right? But given that John is on vacation or already has another partner, then Pradeep and I would be matched, right? So I would just wait.
I always, just to put it straight, I always thought you were too busy to be proposed to with all your partners.
Well, that's probably too, but thank you very much for that. That's very kind. Okay. Okay, so moving on to the rotating proposer game. If there's no questions with this part, now we're going to allow each player to have more than one proposal. Yes. The rotating proposer game, an RPG. The ordering is such that each player can make proposals to all admissible coalitions, all coalitions that contain the player herself, and +1. We need the +1, actually, before the next player in the ordering can propose. Okay, so a player can make many proposals, several proposals. Well, the result is, the main result is every SPNE of a rotating proposer game is Pareto optimal. This embodies the example, more or less, that we had in earlier of a Pareto optimal outcome with the 6 players. But we here are allowing, we have to allow more players to or more proposals to obtain the result in general. The proof is difficult. And to prove it, though, we need actually a number of observations and a lemma. First observation, for any strict subgame and for any 2 admissible proposals, T and T double prime, the resulting subgame is the same whether T or T prime is rejected. Why is that true? Well, if I make a proposal to Pradeep and it's rejected, then, and I have more than one proposal, Pradeep is still there, everybody else is still there, nobody is left, no matter which proposal is rejected. Okay. Observation 2, consider a proposer I and some proposal in the set of proposals that he can make. K is an index over the number of, over the set of proposals, first proposal, second proposal, kth proposal of player I. So let pi ik be I's assigned coalition in the subgame perfect Nash equilibrium of the game that starts with her kth proposal. Okay, here this says, this result says that the, according to these proposals in a subgame Nash, subgame perfect Nash equilibrium, I will propose to her preferred coalitions first. Okay, she proposes to her first or most preferred coalition first amongst those that are in this, amongst all the proposals she makes. And so we have to have, in some sense, her preferences decreasing or constant over the set of proposals that she can make. Well, why? If the kth plus 1 proposal is preferred by I, or the coalition to which she proposes the kth plus 1 time, is if it were preferred to her proposal in the kth time, then in a subgame perfect equilibrium, Nash equilibrium, when I proposes for the kth time, she should make a proposal which will be rejected, right? Because she made, because why? She prefers the next proposal. She prefers the coalition that she would have in the next proposal, okay? And that contradicts theorem 1. In an SPNE, all proposals are accepted, okay? Observation 2, consider a proposer I and some proposal that numbered or in less that occurs the kth time in her possible proposals. Right. So she still has a number of proposals to make. So let pi ik be I's assigned coalition in the SPNE, the game that starts with her kth proposal. Then either the kth proposal is proposed. I did this. Okay. Sorry. Observation 3. If pi k is the SPNE outcome of the game beginning with I's kth proposal and her kth proposal is equal or the same as her kth plus 1 proposal, then pi k is equal to pi k plus 1 for all players, right? If the subgame perfect equilibrium is the same for player I on her kth proposal, If she gets the same coalition, then everybody gets the same coalition, right? If, you know, why? Because it's effectively no change. She's proposed, and this proposal would be accepted if it were made. This proposal is the same, and the subgame that results is the same. Pradeep is looking puzzled.
No, I'm just digesting.
Okay, no problem. Stretching a bit. Okay. Yes. This implies that if the next player, J, in the ordering is not already in a coalition, then the set of available players for J to propose to is the same in both cases, right? Because it's this kth plus 1 proposal just copies the kth proposal. Moreover, and this is a corollary is very important, there must exist a K bar such that the proposals in the K bar and the K bar plus 1 proposals are the same. That's why we need the number of proposals equal to the number of admissible coalitions for player I plus 1. So we can get this result. So we can get at least 2 proposals that are the same. So now we have a lemma. Let's see, I should check the time. Okay. I guess I'm decided right now not to go through the proof of this lemma, because the proof of this lemma takes some concentration and work, and best followed slowly. Okay, so let pi 1 be the subgame perfect Nash equilibrium of the subgame A1, with I proposing for the first time, and let pi 2 be the SPNE outcome of A2, the subgame which results if I first proposal is rejected. Then pi 1 is equal to pi 2. So we've said, okay, some proposals must be the same, okay, and we're saying now that we can back this all up so that the first 2 proposals are the same. Okay.
Myrna, let me take it is my unpleasant task as chair of a session to remind you that you have 10 minutes left.
Okay, thank you. Right. Okay, this is the lemma. This is the proof. Now we can actually prove theorem 2. Pi is a subgame perfect Nash, let pi be a subgame perfect Nash equilibrium outcome of the rotating proposer game. Suppose pi prime is a Pareto improvement. Since these 2 outcomes are different, there must be some players in different coalitions in pi and pi prime, right? There must be. Let I be the first such player. All players for both of these proposals are still available when all players propose. The set of players left to whom I can propose is the same. Let A be the subgame starting with I's first proposal. Since pi prime is a Pareto improvement from strict preferences, it follows that for this proposal by player I, pi prime, is preferred by J to pi j. It's preferred, it's Pareto optimal, so it means all the players who would be in that coalition, or it's a Pareto improvement, all players who would be in the coalition formed here prefer that to what they would get in the other. Okay, they're better off. That's what, you know, so that they would accept that proposal. Pi's first proposal is to the coalition pi prime. All members of that coalition will accept, for otherwise they will be assigned in the resulting SPNE to the coalition pi prime I. Okay, therefore, I will propose to pi prime and the proposal will be accepted. Okay, this implies, though, that pi is not a subgame perfect Nash equilibrium outcome of the rotating proposer game, since the SPNE outcome is unique by theorem 1. Okay, we now have the desired contradiction. Okay, so one thing we've, if there are no questions, one thing that have tried to prove, I think that I want to try to prove it again. The number of proposals allowed by each player can be limited to 3 or 2. Oh, I'm sorry. Again, that happened. Okay. Why do we make that conjecture? Collectively, our results show that only one proposal, the last, is different from the prior proposals. And so in some senses, one would even think maybe it's the case that only 2 proposals would be enough, because the second proposal would be to the subgame perfect equilibrium of the game where a player only gets 1 proposal. Okay, so we need that. That's a credible threat. But we're working on it. Okay. So in summary, the rotating proposer game equilibrium outcomes are individually rational. They implement IMS, an iterated matching of soulmates. So if 2 people really prefer to be with each other, or a group of people really prefer to be with each other, they are assigned to each other. That's an important property. It's obvious, I think. It's Pareto optimal, and we have no delay of forming coalitions, and the SPNE outcome is unique. Okay, from this perspective of decentralized hedonic coalition formation with complete information, this is a strong set of properties. I don't know of any other papers that have this kind of result.
Myrna, if you have, I may be the only person with this need for clarification, but since the main point is the rotating proposer game, which you have introduced to get Pareto optimality, can you just go over what you mean by rotating proposer once more? Just clarify.
Sure. The rotating proposer game is the same as the original game, but each player can make more than 1 proposal. Each player can make more than 1 proposal, but a limited number. The number of proposals is limited or required in our proofs to be equal to the number of admissible coalitions for the player plus 1. So, is that
what's rotating?
What is what?
What's the rotation referring to?
What's the location difference?
No, rotation. You said rotating.
Oh, rotation. Oh, okay. It may not be the best word. Okay.
Myrna, can I chime in? So it's a reference to the like a rotating dictator mechanism, where each player in turn gets 1 shot to pick their favorite coalition or whatever it is, their favorite item if it's an allocation problem, and then we move on to the next dictator. So that's where the rotating part comes from, just a allusion to rotating dictator.
I see.
Okay. Okay. Continuing. Now, we think about implementing this as a mechanism. The one thing the rotating proposer game lacks is it's not necessarily strategy proof. It's not necessarily that players that will state their true preferences. It's subject to manipulation and deception. So if we make this a mechanism, right? People may report different, not their true preferences. So if they don't report their true preferences, you don't necessarily get a Pareto optimal outcome. So, yeah, but there's some positive results. If everybody, right, if everybody reports their preferences truly, right, we have the same good properties of the rotating, inherited from the rotating proposer game. And on the class of iterated matching of soulmates complete preferences, that is, if everybody can be matched as soulmates, then rotating proposer mechanism yields a unique core coalition structure, okay, as does, of course, the game. And what the domains on which everybody will is motivated to report their true preferences include other well-known restrictions on preferences, such as the top coalition property, right? Which means that everybody has soulmates. That implies that everybody has soulmates in every possible coalition to which they could belong. And the common ranking property, so everybody ranks players the same. So that's on the positive side. So we wanted to do some, yes, Pradeep.
So you have 1 minute left.
1 minute left. So we tried to do some simulations and get some results, and they're in the paper. And we find that in these simulation results, very few players, small percentages, are the only players who have an incentive to misstate their preferences. And they have good properties. We can compare the rotating proposer game in all of these, and the rotating proposer mechanism is in yellow, and the serial dictatorship is in dark blue, and we can see that our mechanism outperforms in all of these examples of the serial dictatorship. Okay, now my last slide. Here it is. Yes, many thanks to the organizers and all who to all who attended this presentation. Okay.
Thank you very much, Myrna.